Okay, good morning, everyone. I welcome you all to the second webinar of the Simulations with Design Builder webinar series. I am Amanda, and I will be moderating today's session. In this webinar, we will discuss how to populate construction details for solar, thermal, and daylighting calculations using DesignBuilder software. We will also discuss how to conduct sensitivity analysis to optimize your building envelope and how you can use these results from your analysis to choose the right kind of walls, roofs, and shading devices for your building. These simulation webinars are scheduled to align with your deliverables. The previous webinar and this webinar are relevant to your first submissions. Previous slide, please, Mansi. Yeah. So before we begin, I would like to thank our program supporters and affiliates for this year. These organizations have provided immense support to Solar Decathlon India and catalyze our transition to a net zero future. Next slide, please. So today we have with us Mansi Parikh and PC Thomas. Mansi is a senior sustainability consultant working in the field of sustainable design. She has key qualifications in the field of passive designing, low energy cooling and HVAC systems, lighting and daylighting design. She has worked on various projects with goals leading to net zero energy, water and waste. So hi Mansi, good morning.
Hello, good morning.
We also have PC here. PC Thomas is the founding director of Team Catalyst and also an adjunct associate professor at University of Sydney. He specializes in integrated building design using simulation tools to assist in design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulations, energy auditing, energy efficiency in buildings, and solar energy. Hello, PC. Good morning.
Hi, everyone.
Yeah. So before we begin this webinar, we will have our communications person of Solar Decathlon India, Janani Venkatesh, who will give you a quick talk about communication strategies. So over to you, Janani.
Yeah, thanks, Amanda. Hi, everyone. I'm Janani, and I'm just taking a few minutes to check in about your communication strategy. I see that some teams have already begun creating their social media profiles, and that's a good start. And others start building your brand and networking with your audience. Tell others about what you're learning and what you're doing in the challenge. You can add more team members to your team. So try and get a team member from a communications background who can take care of your outreach efforts. So this is an opportunity for you to scale up the impact of your work. And also remember, the jury will evaluate you on your outreach efforts for the 10th contest of the decathlon, which is communication. So yeah, start telling your audience about how you're making a difference and addressing climate change and how meaningful your learning is. So the COP26, the UN Climate Change Conference, will start on November 1st, and they will discuss the progress on the Paris Agreement to cut down on emissions and combat climate change. Greta Thunberg has already begun her activism a month before the conference. So you can take this as an opportunity and talk about how your project will fit in this context and how you are contributing your efforts by designing a net zero building. So I'll just leave you with that. Thank you. Back to you, Amanda.
Thank you, Janani. So now we will begin first with Mansi's presentation. And to all the participants, please feel free to send in your questions at any time during the session. And we will take as many questions as time allows during the session. And with that, let's get started. So over to you, Mansi.
Okay. Thank you. So in this presentation, I'll be discussing the findings for studies done for Ashoka University project, which is going to be a net zero development. The campus is located in Sonipet, Haryana, which falls under the temperate climatic condition. We discussed about the climatic analysis in the last webinar. So in this part of the webinar, we'll be discussing about the importance of envelope design, designing for shading, facade, wall construction, and window typology. This image shows the irradiation on the facade in north, south, west, and east direction. The range varies from 200 to 1200 kWh per square meter per year, where blue depicts the lesser amount of irradiation falling on the facade, and the red depicts the higher amount or maximum amount of irradiation falling on the facade. As you can see in the images, maximum amount of irradiation is falling on the south facade, east facade, and the west facade. Hence, we provided shading recommendations for south, west, and east facade. Shading is required for solar control and to reduce the glare probability in the space. In this image shows the Sunpad diagram for the Sonipat. Shading to reduce heat gain is required to be provided in the summer months from 9 a.m. to 2 p.m. Again, while shading is provided for glare control to reduce the glare probability from the low angle evening suns. Glare for the section shown on the right, 1.2 meter window width with 2.6 meter of window height is provided. This is for a typical classroom. So what we did was, it was divided into two parts, that is the day pane and the view pane, and the individually shading was provided for each of the panes. So here we have an internal light shelf, and these are the fins. Combining this, we achieve the solar control as well as the glare control. The images in the left shows the facade options for different directions. The upper options are the single glazing unit with no shading, with shading, and the case with shading, as well as the wall insulation on the inner side. Similarly, these options are with the DGU, that is double glazing unit, without shading and with the insulation. So what we did was, in these options, we worked out for all the direction, that is north, south, west, and east. The graph on the right depicts the percentage reduction in the peak cooling load, which actually relates to the HVAC system sizing. And the lower graph shows the reduction in annual cooling energy. Cooling energy in this building accounts to almost 70% of the total energy consumption. Case 2 and case 5 both works the best for both single as well as double glazing units, since they have the maximum amount of reduction in terms of peak cooling loads and in terms of annual cooling loads. However, case 5, which is a DGU with insulation as well as shading, works the best in this case, which has maximum reduction of annual cooling energy and peak cooling energy in all the directions. Now, this is also a way to look at shading benefit and analyze the results. The image on the top shows the irradiation falling on the facade without shading, and the one on the bottom shows the irradiation on the facade with vertical fin shading. By providing shading, average irradiation on the facade can be reduced by 25%. Here you can see it goes from 140 kWh per square meter per year to 105 by providing the fins. This graph shows the wall U-value sensitivity analysis done for north facade, where wall U-value is varied from 2.4 to 0.2 watt per square meter per year, where 2.4 is without any insulation and 0.2 is the brick wall with 125 mm of insulation. All the other parameters are kept constant other than the U value. The difference of these U values is compared in terms of annual cooling energy, which is the maximum load component in this building. cooling demand is the maximum consumption. The U values are represented on the x-axis and the annual cooling load is represented on the y-axis. There is a linear reduction in annual cooling energy, which can be seen here. However, insulation required to achieve this U value is significant as compared to, so here 0.2 works the best in terms of reduction in annual cooling demand or annual cooling load. However, to achieve this U value of 0.2, we have to provide much more insulation as compared to 0.4 U value, which will increase the cost to almost 3 times. Also, it has very little reduction in terms of annual cooling load, in terms of EPI. So for this project, we decided to go for U value of wall of 0.4 watt square meter per year. Now, it's not only the energy or peak cooling load, it is also the thermal comfort of the occupant which is related by providing insulation in this space. So the U value has also impact on the thermal comfort. Both the graph shows various temperatures across typical summer week. The one in the bottom shows the case with insulation, and the one on the top shows the case without insulation. The x-axis represents the hours of the week, and on the y-axis is the temperature. The yellow line shows the external temperature, dark green shows the ambient temperature, that is the dry bulb temperature, red shows the internal surface temperatures, and the light green here shows the resultant temperature, which is also what you actually feel, the felt temperature, which is average of dry bulb temperature and the radiant temperature. So here what is observed is in the case without insulation, the surface temperature goes 1 to 2 degrees higher as compared to the case with insulation, the internal surface temperatures, which also has an impact on the thermal comfort of the occupant. Hence, it was decided to provide the insulation. The location of the insulation on the wall, probably on the inner or the outer side, is equally important. This will depend on whether it is naturally ventilated building or it is an air-conditioned building, whether it is 8-hour operation building or it is conditioned for 24 hours of the day. Whether it is internally loaded building, where there are significant loads from the people and the equipment, or whether it is externally loaded building, where it is more gains because of the envelope. So here it was observed that external insulation was selected for this wall assembly since the internal surface temperatures were lower in this case. Here you can observe that. The variation on the internal insulation was much higher as compared to the one on the external wall. Based on the insulation thickness, options for the wall constructions were given to the client with different construction materials as well as the insulation thickness. There were options for brick, AC blocks, concrete blocks, and hollow concrete blocks. Amongst this, AC block with 200 mm thickness had the least amount of insulation required, that is 40 mm, and the others had almost 60 mm insulation required. Hence, so this would have the least amount of wall thickness. As you can see, these are the construction assemblies which were proposed to the client for brick, AC, concrete, and hollow concrete blocks, which had cement plaster, concrete blocks, and XPS, and the cement board requirement on the internal side. So only 40 mm insulation was required for AC case. So with a thickness of 270 mm, so the client went with this case for AC block construction work here. Now, window to wall area ratio also has a significant impact on annual energy consumption of the building and thermal comfort of the occupants. For this case, this is again a facade where we go from top to bottom. There are different WWR for 20%, 40%, and 50%. We also did a quick check on the impact of annual peak cooling load as well as annual energy consumption demand. And based on this, WWR for 40% was selected for this building. So now, after deciding the WWR, specifically for naturally ventilated spaces, percentage of openable window area was decided, since that is also important, right, while we are designing. So percentage of operable area was decided by doing this sensitivity analysis. Here, so what happens is, these are the two cases. Smaller windows can be kept open during the night time, okay? But say if it is 0.6 or if it's a 2 feet window. But however, larger windows have to be kept closed during the night time because of the security reasons. So here, there are two cases worked out. Case one, which has only single-sided ventilation in the space and the larger openings. However, we have case two, where we have much more added smaller windows, where this window is broken in two parts. And then we have added one more window here to improve the cross ventilation in the space. So in this graph, as you can see, on the x-axis is the operable area of the window, that is based on the percentage of opening, whether is it openable or sliders. So if it's slider, we have 0.5% of operable area, where openable we can almost achieve to 0.9 side hung windows. And this depicts the percentage of comfortable hours. So as you can observe, the case with cross ventilation, which is the case 2, works better as compared to the single-sided ventilation, because it has more number of hours which are comfortable. So it is almost 10% increase here, as you can observe. However, beyond the point, it was observed that however, after increasing the percentage of operable area, there is very little or very insignificant amount of increase in terms of comfortable hour. So hence, we recommended case 2 with percentage of operable area of 60%. So in this, we covered about building envelope, walls and the windows, typology. And with this, I finish my part and I'm open to questions.
Okay, so thank you, Mansi. So participants, please send in questions if you have any questions for Mansi. We have 2 questions. Let's take up one by one, Mansi. Okay. So Mansi, in your first question is, in your presentation, what is resultant temperature? Is it the same as operative temperature?
Correct. So resultant temperature, I would say, is an operative temperature, which is an average of air temperature and the radiative temperature.
I can confirm that in DesignBuilder, you will get operative temperature, which is exactly what Mansi said, which is the average between the air temperature and the radiant temperature.
Right. Okay, thanks, Mansi and PC. Moving on to the next question, the sensitivity analysis had so many U values simulated. Is it necessary to do so many, or can we do 2 to 3 alternatives only?
Doing multiple U values actually helps us in seeing the, seeing the curve of the graph. We will see, generally, we see a point of diminishing returns, where after beyond a point, reducing the U values beyond a point, say 0.2 or 0.3, the amount of reduction which we get in terms of annual cooling energy or in terms of peak cooling load, which would help us in system sizing, is reducing. So I would say it is good to have a sensitivity analysis. It gives us a good amount of information, and based on that, after that, we can say do a couple of them. Say if we come up for say 0.4 nearer that, then we can take we can do this for 0.6, 0.4, and 0.3 probably, and then based on that confirm. I would say.
Mansi. Next question is, the case discussed here, is it area specific?
Yes. As in, it would be great if you could elaborate on this questions, Amanda.
Sorry?
What does it say exactly? Can you repeat?
Yeah, so Shivani Bahuguna wants to know if this case study that you have shown is very area specific. So
I believe that would be definitely, if area specific as in climate specific, yes, it would vary with across the climate zone.
right, yeah. So yes, definitely it was area specific based on your location. You know, you use your climate weather analysis and then do analysis based on those weather data.
It would be case to case. Agree.
Next question we have is the irradiation analysis possible in DesignBuilder? I think this is something that PC can answer. Yeah.
Yes, I'll show you a picture of the so incident solar radiation analysis that Mansi has showed in DesignBuilder.
So yes, we'll get to see that soon. Then next question we have is again from Shivani Bahuguna. Window wall ratio case need to be verified for every location? Does window to wall area ratio needs to be verified for every location is the question.
Okay. So see, across the verified for each location, I'm not okay. You can have, however, something for various climatic zones, you know, say something for hot climate, hot and dry climate, and something for the colder climate. Because the amount of irradiation or the amount of heat gains would be very different for both of those climate types. So I would say there would be, it might vary a little bit. However, in terms of location, however, it would definitely vary in terms of climate typologies.
So Shivani, another thing is that, you know, in your first submission, we asked for a shoebox analysis, right? So window to wall area ratio can be one of the analysis that you could include in your shoebox analysis, where you kind of put in your, you know, weather data and then figure out, you know, which ratio works with the best. It can be in terms of, you know, energy reduction, you know, things like that. So you can do more analysis based on the wall to window area ratio. Next question we have is from Yash Shinde. For cold regions, will this method get completely opposite of what you have shown right now?
We'll have to check for that.
Right. So you can use your weather data. And then, you know, based on your weather data, you can do various analysis. Okay. Next question is, does WWR change for orientation of window in each wall?
I would believe yes, because see, as I showed in the irradiation analysis, that the amount of shading which you would be requiring in north would be very much different as compared to what you would require in south. So, you know, it depends on the kind of spaces you have. It depends on it would be very project specific. But one thing I can be sure of is it is easier to shade windows in north as compared to south. This is more related to the hot climates, you know. So that depends on you. How do you want to proceed? You want to make it difficult or as easier for you to shade the windows?
Yeah, so another thing is that, you know, in your SLMs in passive design module, you might have seen, you know, we talk about radiation received on each direction, how radiation received is different for each direction. So, you know, based on that, you can come up with various WWR for different directions so that, you know, you minimize the radiation, you know, in your building, received by your building. Yeah.
Could I also add, Amanda, that there will be some effect of self-shading within the building. So you may have to watch for that. If I can just share my screen.
Sure, yeah.
I think you have to allow me to do that.
Mansi, could you stop sharing?
Yeah, I've stopped sharing.
Okay. Let me try again. No, it keeps telling me, now I think it may actually help me to. Here we are. So here's a DesignBuilder model. And I have just run it for the month of March. So it's sort of neither winter nor summer. And you can see that because of the self-shading between between one side and the other, that there is a difference in the amount of radiation that is being received by this wall compared to this wall. And your design will probably need to do some analysis to figure out what's the best way of looking at that. Okay, so what Mansi has said, all of that is very relevant for your, and you can do all of that analysis using DesignBuilder.
Right. So we have many more questions, but we'll take one last questions and then we'll continue with PC's presentation. Then we'll come back to these questions again. So this question is from Pawan Kumar. How to calculate window wall ratio? Is there any particular standards to be followed on different types of building?
I would say there are no, I don't believe there are standards for a particular kind of building. However, ECBC does specify, that is Energy Conservation Building Code, does specify that your WWR has to be less than 40% or 60%. There is a requirement. So you could refer to those standards. But it is the calculation is simple. It is window area upon the wall area, total amount of window area on a facade divided by the total area of the facade of the wall area.
I believe DesignBuilder do give this results, right, PC?
Yes.
The results section, yes, yeah.
Yes, you can do templates which have already got some pre-built window to wall ratios, and I think Mr. Vaidya just put an equation in there, which is, I think, correct as well. So
yeah,
there are many. Yeah.
All right, so thank you, PC and Mansi. So PC, let's get started with your presentation now.
Okay, thank you. So I have about 45 minutes.
Right, yes.
Okay, thank you. So let me start to share my screen. Give me a second, here we go. Okay, so last time we covered two areas. So we covered, let me see, sorry, I've got the wrong, yep, here we go. So last time we covered how to review results. And then we also covered how to do geometry, if I remember right. And when we covered geometry, many of the things that Mansi showed, those window shading, shelves, sun path diagram, we can do many of those things. And hopefully as we go along, we can continue to do that. Today, what we'll do is we'll do two more topics. The first topic we'll address is actually extremely relevant. Thank you very much, Mansi, for your lecture. It will actually show you how to construct a wall and how to work out the U values, etc., for each wall and floor and roof and so on. And the other one we'll look at is what are the other model inputs that we will need to incorporate so that our simulation actually starts to provide some useful data. So with that introduction, let's proceed. I'd like you to look at two pieces of PDF, which I'm sure you have been provided by Solar Decathlon. The first was the training webinar list. So we're going to be doing number 3 and number 4. Okay, so if you've got that available to you, then that's useful. And we'll be following, if you remember, the workflow that I've given you for the first Design Builder model. We'll be looking at sections 2, really, model input data. And there we'll be looking at how to set up constructions and so on. So the first thing, and I'll continue to use the model that I had built or shown you last time. So that model, if you remember, is a very simple, it's almost a shoebox, but you can call this one a UBox model if you wish. So there are 2 identical floors. There's a ground floor, and the ground floor has got one bedroom area, 1 living room area, and 1 kitchen area. And it's very simple. It's very useful for teaching. And there's exactly an identical floor on the top. The only difference is that between the first floor and the ground floor, I've cut a hole in the slab so that it allows me to put a staircase. So if I was going to have a look at the building, and we've done this last time, so I'll just show you very quickly. If I have this building in the render view, by the way, I'm using Delhi, so the sun charts are correct for Delhi. If I just have a look at maybe I take I'll cut a section from the top. Yeah, here we go. So that's the slab. And if you look carefully, you will see the slab has got 1 hole just over there to allow a staircase to be modeled. I don't need to model the staircase as such, but I do need to model the hole that has been constructed for the staircase. Okay. So let's go back to what we're going to cover today. Now, if you look at the PDF that was provided to you about the first model, we're going to do some settings. Okay, so these initial settings in Design Builder are quite important before you do any simulations. So you can see here, I've listed these out and I'll show you how to do them. And it says here, uncheck this similar windows on surface. And that simply means that when energy simulation programs were first developed, computer power was scarce. So what they used to do was, if on a wall you had identical windows, they would just take 1 window and then model the impact of that, and then multiply that impact across. Of course, nowadays computers are much more powerful. And if you're doing a daylighting analysis, this is not a good way to do it. And if you're doing a natural ventilation analysis, this is not a good way to do it. So now, by doing this setting, you're telling Design Builder, model every window separately, okay? The second one is to do with how many times in an hour should the equations converge, okay? So the more times you make the equations converge, the more accurate it is, but then the more time it takes to do a simulation. So you want something reasonable. So we have decided on 6. So it will do 10, every 10 minutes, it's going to do a convergence, right? Again, once you set it, you can forget about it, but it's good to set it in the beginning. The other things that you may want to look at, and you can reset this obviously once you've started, are different units to describe how occupancy in a space is happening and how you want to account for the heat gain from equipment. So anything that's in your space, it could be computers, fax machines, TVs, anything that produces heat, a toaster, microwave ovens. You might lump it all together into some sort of cooking devices in the kitchen and provide some measure for that. And then for lighting, there are also different ways of setting it up. So let's do that first, and then we'll go on to doing constructions. I'll keep looking at the chat, but Amanda, if you want to just keep your eye on that, and then at the end of the session, we can take some questions.
Yeah.
So these options we will set under this spanner icon, which is called model options. And model options only deal with setting the parameters for this model, the model that you're working on. It doesn't change the way DesignBuilder as a whole works. It's only for this model. So we'll go to this model options tab. And when it opens up, you can go first to this advanced tab. And you can see here that you want to make sure that this box is unchecked. Okay, so once it's unchecked, DesignBuilder knows that it has to model each window separately. And then under this data tab is where you get these options to decide how you want to look at modeling or inputting. Number one, occupancy. So you can say, either you can say the number of people per space, or you can say the area per person. So many square meters per person. Sometimes you might want to give an occupant density. So an occupant density is, again, 0.1 person per so many meters squared, so on. Now, if you're doing residential buildings, probably area per person is a good measure. Sorry, a number of people is a good measure, not area per person, sorry. But if you're doing something like an office building or an education building, then possibly within your national building code, there'll be some area per person. Now, typically in Australia, for an office building, we would say 10 meters squared per person, right? So if you've got a 100 square meter room, then 10 people are can be fitted into that as per the code. These numbers are different. In India, I would suggest that the area might be smaller. I have seen 8 meters squared per person and as tight as 5 meters squared per person, but you might need to go and have a look at what's the correct value for you. Now, don't worry about the occupancy latent gates. For the present, it's okay to leave it as dynamic. That simply means that Energy Plus has got an internal model, and it looks at what's happening within the space, and then it decides how much of the heat generated by a person can be broken down into what we call sensible heat and humid heat. Latent heat is humid heat, right? So how much moisture are you producing in terms of heat? In terms of equipment and lighting gain, I do suggest you put it initially at least at power density, which is simply a watts per meter squared. But you have the options to put the absolute zone power. So if you know exactly how many watts of lighting are in a zone, or how many watts of equipment, maximum watts of equipment there are in a zone, you can go and put that in there, okay? So those are the adjustments that I had talked to you about. So I'm just going to leave it over there for now and press that, okay? So we've done that. Now, if you remember, and if you go and see the presentation that I showed you was on YouTube and also at the DesignBuilder Australia website. It's about, let me show you. Yeah, it's about a YouTube presentation that I'd done on introduction to building energy simulation. And I showed you some slides for that from at last time, okay? So a couple of the slides that I'm going to concentrate on this time from that presentation are useful to revisit. Okay, so the first one is this slide, where I spoke about what are the different components in a simulation model. Okay, and I said the first one was that you actually model the geometry of the building, which we did last time. And we describe the construction materials that go into that model, which is what Mansi was talking about earlier today, right? So we're going to be looking at that. Now, in addition to the materials performance, you must also provide the performance of the window, okay? And windows are interesting, okay? And when we start to put those performance parameters in, then we'll talk about that. So let's go ahead and look at the materials for the opaque part of the building envelope. So the walls, the floors, the roof, partitions, slabs, all that kind of stuff. So if we go back to our DesignBuilder model here, you can address all of that underneath the construction tab, okay? So just to draw your attention, I'm at the building level, which means that as long as I haven't gone to a specific wall or a specific zone and made a change there, any construction material I put at the building level will flow down that data tree. So all the floors, the walls for each of the bedrooms, kitchens, living areas will all have that same construction, unless I go and change something at one particular level. In that case, that one won't change, all the others will change, right? So let's put it at this construction level, at the building level, sorry, right? So when I click on the construction, you can see here that I've got a template, and this template says India uninsulated concrete construction. Now, I built this when I did a training program at CEPT, I think in 2014. So those constructions are still here. They were a good one to start with. And then we can test a couple of very quick outputs from that. So the way DesignBuilder handles construction is that you describe these elements. Okay, so say external walls, below grade walls, flat roofs pitch roofs that are occupied or unoccupied, internal partitions, ground floors, external floors, internal floors. They all have a meaning within DesignBuilder, okay? So what is that meaning? So let me show you that. What I've done is within the online DesignBuilder help, so you can just Google DesignBuilder help version 7.0, that's what I've got. I searched for the word combined constructions, okay? And this combined construction actually shows me how DesignBuilder looks for constructions, right? So if you look at this diagram, it's quite explanatory. So your external walls are these brown walls. So they are the walls that connect or isolate the building from the outside climate. So here's an external wall, here's an external wall, there's one over here, there's one over here. Fairly logical, right? It knows what a roof is. So this is a pitched roof, and this pitched roof is unoccupied. So if you have provided a construction for an unoccupied pitched roof, that is what it will apply to this element, okay? It will then know that there is a ceiling, and this ceiling is not in a conditioned space, so it's called a semi-exposed ceiling construction. So it will put it over there, okay? If you look at this one here, here's a flat roof. And so if you've described a flat roof construction, that's what it will apply. Okay, and if you haven't described one, then whatever was the default construction, it will apply that. Okay, so internal partitions, as long as you've described it, it will apply that. And then there are three kinds of floors, so you need to be aware of that. There is a ground floor. So this floor is in connection with the ground. And that's quite different from the rest of the model, because the ground temperature, or the deep ground temperature as we sometimes call it, it doesn't change a lot during the year. Now, between summer and winter, there might be a 3 or 4 degree change across the entire year. It will change very slowly. There'll be a big phase lag between it. So, you know, the summer temperature will actually reflect in the winter, or at least partway through, 2 or 3 months phase delayed. And therefore the heat transfer that's happening is quite a different kind of heat transfer. Okay. We have simplified models. The actual heat transfer process is 3-dimensional, but we sort of simplify that into a 1-dimensional process. So you need to be quite careful about that. Okay, and I'll show you what to do in a minute. But that's something to be aware of. So this is called the ground floor construction. This is an internal floor which connects 2 zones within that building. Okay. And you have something here called an external floor, this deep blue one. Now the external floor sees the ambient temperature, it sees the ambient wind speeds, but it doesn't really see any solar radiation. It might see some reflected solar radiation, but no direct solar radiation. So that's why this external floor is treated differently within the heat transfer calculations. Okay. Now, you don't need to sort of go and place these things in the right position. You need to describe what they are, and DesignBuilder pretty much does the rest. Okay. The DesignBuilder will calculate, okay, what's the internal floor area between zone A and zone B, and it will work out that area. It will show it to you on the tree. Okay. So you can read, look at this diagram and sort of get to a really good understanding of most of the things within DesignBuilder. Some things you may still need a little bit more help, but most of it is described there. Okay. So here's an external wall. And so now we want to understand what kind of wall do we have? What kind of wall should we be looking for? So if you examine that, so I'm going to double click on this wall, and then if I select this icon, which means edit selected data, it will actually show me what's the construction of that wall. Okay. And here I can see that the construction type is layers. I have asked for 3 layers within this wall. There is some cement plaster, there is a concrete block, and there is a second layer of cement plaster. So this is 13 millimeters. That's 100 millimeters. This is 13 millimeters again. Okay. So if I click on the image here, then it allows you to quickly check that you've got the, the right set of layers in the right order. So there's the outermost layer. This is the inner surface, which is internal to the zone. Here's the cement plaster. Here's a concrete block over there. Now, if I then click on this calculated button, it will actually work out for me what is the system, the U value of that system. Okay. So if I look here, the U value of the system is 2.4, 2.5, say, right? The R value, which is the inverse of the U value, is 0.4. Okay, and sometimes it's only a convention, but in some countries, like in Australia, we will use R values for opaque construction and U values for window construction. You don't do that in India. In India, you generally use U values for everything. So just be aware of that. Okay. Now, there's an interesting one here. It says here, these are the values with no bridging, and these are the values with bridging. And it's calculating that using an ISO standard, an international standard, right? What is this bridging? I'm sure you've already been taught that, but essentially it just means that if you had an insulation layer, then if there was a material that penetrated through that insulation layer, so it connected the outside and the inside of that insulation layer, then it derates the performance of the insulation because you have a highly conductive penetration from one side to the other between and through that insulation layer. So you want to account for that derating, and if you do, then the bridging comes into effect. Okay. Now, just be aware that the simulation is not done for the bridged value. It's done for the no bridged value. So one way of working it out is that you work out what is the U value once you've included the thermal bridging. So, you know, these 2.4 might actually go up to say 2.7, and then you model that. So you put the 2.7 as your no bridged value, and DesignBuilder Energy Plus will do the calculations for that. Okay. So that will give you, and you can, behind each layer, there's a material. So here's a cement plaster material. If you open that up, you'll find that DesignBuilder has got an enormous built-in database. Okay, so that database comes from SIBC, from ASHRAE, some values from ISHRI, things like that. There's a huge number of different things. Like, for example, if you looked at, say, I think there should be one on concrete. So if I open up the concrete, you can see there's a huge number of different kinds of concrete, right? So anything that is green or black comes from different SIBC, ASHRAE, all those kinds of areas. Anything that you see in red is what I have created, a custom copy, okay? So if you don't find the material that you want, you'll be hard pressed to find it. But if you don't, then you can always bring your own, put your own material in there, okay? So for example, here are sands and stones and soils, and you'll find lots of different options available to you. Okay. So have a look through them, and you should be able to find all kinds of things. There will be, if you look carefully, there'll be adobe. I believe there's mud fusca somewhere in here. So you can have a look. If you don't like the material that's here, you can go and add your own material. Now, behind each of these materials, so let's go to the cement plaster material that we were looking at, cement plaster mortar. Now, which one is it doing? Here we go, this one. If I actually look at that material itself, there's a fair bit of data behind that as well. So each material comes with its physical properties. So, you know, conductivity, specific heat, density, and that allows the model to calculate this dynamic nature of the building fabric storing and releasing heat. Within all these energy simulation models, there's at least 7 or 8 hours of history of how heat was stored by this from the sun or from external ambient temperature within the building fabric, and then as the temperatures cool during the nighttime, how that heat is released and where it is released to. So it's quite important to give these detailed properties, okay? You can give a simplified R value, but an R value completely negates the thermal mass impacts. Okay, so you should provide these conductivity, specific heat and density numbers if you want to create a new material. The only exception to that is if you are using an air layer between a construction. So for example, a very typical Australian British construction is 2 layers of brick with an air gap in the middle, a cavity brick construction. So in that sense, then the air gap is usually described by just an R value. Okay. Now you can read about all this stuff. If you pick up any of the books on this, you'll find it. Okay. Now, if you are interested in vapor and moisture calculations, there are models for that, but it's the fastest way of slowing down the simulation. It really slows down the simulation. So unless you really have a need for that, try and avoid that. But of course, if you are using some hygroscopic material and you want to see how it controls the humidity inside a space, that's probably worth checking out. Now, there are some other properties here as well. Okay, so in addition to those properties that you saw, there is thermal absorptance or emissivity, there's solar absorptance. So if you want a particular solar absorptance for a wall, then you can adjust the solar absorptance for the outermost layer of your construction. So if you've got a dark wall, you can make it a high solar absorptivity. You've got a light wall, you can make it a lower solar absorptivity. And there is a visible absorptance. Now, if you remember, your basic equation is that transmittance plus reflectance plus, what's the other one? Transmittance and absorptance is equal to 1 at any wavelength, right? So in terms of an opaque material, you don't have any transmission. You've only got reflectance and absorptance, so you can work out if you have absorptance, the reverse of that is reflectance, or the 1 minus of that is reflectance. So you can adjust that there. If you're doing daylighting calculations, then you should look at this reflectance, particularly for the inside material, because that is what adjusts the daylighting within a space. So a dark wall has got a low reflectance, a light wall has a high reflectance. That will change your daylight analysis outcomes, okay? So if most of the materials that are here have got appropriate values, if you are creating your own, be aware of these things, okay? If you want to model a green roof, you can switch that on. Again, you want to go to the outermost layer of the roof and then work from there. And there's a whole bunch of things that you can adjust over there, okay? If you're working with embodied carbon, you can put some data in. Remember that the data over here is probably UCO specific. It gives you the source, EcoInvent version 2, whatever. So if that's not appropriate, you will have to find something that you like. If you have a phase change material, you can call it that, and then you can provide data. And just to let you know, there is already a whole series of phase change materials built into DesignBuilder. Now, I'm not sure these products are available in India, but there are some competition products, and you can try and figure out whether some of these are equivalent to the competitive products there. So there's a series of products here that are already built in with the phase change impacts on that. Now, if you want to do phase change materials, read the help book because you have to make some different settings to allow that phase change impact to be taken care of, okay? I keep telling you, and I'll continue to keep telling you, if you don't put the right settings in, it's garbage, and garbage in is garbage out. Your results will not have any bearing with reality if you don't adjust all these things correctly. Okay, so the one thing that I haven't covered is how do you make an adjustment or how do you make a new wall, okay? So let's do a quick thing. I'm going to close this one off. this is my wall. Okay, I've put here a flat roof construction, which I've also put for the pitched roof and unoccupied and occupied. In this model, there's only a flat roof, so that's what will get used. I've used some uninsulated concrete blocks as the partition. I've got a ground floor. Let's have a look at that. I think that's also a slab, just a concrete slab on grade with some probably a screed on the top. We'll just have a look. Yep, so you can see 2 layers, concrete, 1,800 kg per meter cube, 150 millimeters, and then on top of that, a 1 inch of terrazzo, right? Which is fairly common construction in India. So those are what I've got here. So what I'm going to do is I'm going to make a run. Again, I'll just make it for March, okay? And then we'll have a look at some temperatures, and I don't think I've got any air conditioning setup. It's set up as a naturally ventilated model, so we won't get any energy numbers, but we will get some temperature numbers. Okay, so in fact, yeah, it doesn't matter. We'll do a quick simulation. That's the easiest way. Amanda, how many minutes do I have left?
10 minutes.
Okay, all right. I'll move it along quickly. So if I do a very quick run, then it's using those material properties to calculate what are the inside temperatures and what are what's going on within the building. Okay, so I let it do the run and I let it pick up the variables, and actually I let it upload the results back onto DesignBuilder. So I'm only running the month of March, so it's a short run. Okay, and so from the 1st to the 31st, we've got completely uninsulated walls, and I think I've got very simple single glass aluminium frame windows, which we'll do immediately after this, and we'll see what's coming out. I'll save these runs as well, so when we make some adjustments, we can see what's going on. Okay. Now, to make a change, which we'll do as soon as I've done this, what you need to do is we can do one of two things: either make a completely different, select a completely different set of constructions, or you can take one construction, and we'll do that to the roof. We'll take the uninsulated roof and we'll add an insulation layer, and I'll add it to the outside of the roof. So it's actually above the concrete slab. And then on top of that, you need to put waterproofing and something. And then we'll just do another run and see what is the impact of that one. And we look at the impact of the inside equivalent temperature, operative temperatures, what Mansi was talking about, for the 2 runs. So that'll give you a good idea as to how to use DesignBuilder for doing that sort of analysis. Okay. Okay. So I won't worry about this right now. What I will do is I will go to the results folder, the Energy Plus folder, and I will copy just this ESO file, and probably I should just copy the HTML file also, so if you want to see it afterwards, and I will save it somewhere. So that's a good point. Where should I do that? No. Okay. Oh yeah, I can do this here. So this is day 2. I'll just paste it here. And I'll call this my uninsulated run. Okay, so this is my base case 00 uninsulated. Okay. Now, what I'll do is I will go back to my edit tab. We'll go back to constructions. And as I said to you, we'll change the roof. So this roof, flat roof, okay, Now, the easiest way to do this is to make a copy of this. So I'll make this a copy. And what I can, where am I? Yeah, sorry, edit that. Yeah, and so instead of calling it an uninsulated one, I'll now call it insulated. Okay, and what I can do is I will add a layer, and what I'll do is I'll add a layer on top of the concrete slab. Hang on. Yeah, so I'm going to insert a layer. So I'm going to add it to the outside of layer number 2. And you can play around with these things. I'll change the material after I've added the layer. So now you can see I've got 4 layers. Okay. I've got my medium weight concrete and my cement layer here. This layer I will change. And then I remember listening to Mansi, and she said that she had used an XPS sheet. So in my insulating materials, I will go and find an XPS sheet. Here we go. So I'm going to put that on. And that's 200 mm. That's pretty thick. So what I might do is I might change that to 100 millimeters. Okay. So if this is what I've done, and if I do the calculation, you can see that the U value is now 0.3. Now I should have told you what it was before, but I suspect it would have been around the U 2.5 or something like that. And just to double check, I just want to make sure, yeah, so the outside is a clay tile. I've got XPS sheet, medium weight concrete, and then a plaster on the inside. Okay. So I will say, yeah, I'm happy with that. Apply that. Okay, so I've got that change. Now I know that in my model, I only have a flat roof, so I'm not going to worry about anything else. That's the only change I have made. Okay, so I'm going to save this file. And then run the simulation again. So let's do that. Okay, I'm just going to run it again. And this time, as soon as it finishes the simulation, I'll actually cancel I won't let it load the results back. I'll just pick up the results from the folder. Okay. Okay, while it's doing that,
while we wait, should we take a few questions up?
That's what I was thinking. If you have any questions, Amanda, let's do that.
Yeah, right. So we have one question from Dhruv. How can we go about using bamboo as a material for walls and roof? And how can we do different types of bamboo with different bamboo species and forms like corrugated sheets and flattened bamboo, etc.?
Okay. Yeah, that's very good question. It's not very difficult. Okay, so if I show you, the first thing that you probably want to understand is, how does your material or your construction system look? Okay, so you need to figure out how you're going to represent it. What are the layers that you want to use? So you want to be sure of layer 1, layer 2, layer 3, layer 4, like that, for wherever we are. I am fairly sure that within DesignBuilder, there's already bamboo. We'll have a look at that. And you can pretty much bring it in, make sure that you have it as the correct layer. Now, you'll probably have some, you might have some sort of plaster or mud or something as the other layers. Just make up your construction, including bamboo, and there should be no problem. There's wood anyway described there. as long as you find the properties for bamboo, that's really all that you require. So it's not a very difficult thing to do. Okay. So let me just pick these quickly and then we can finish this off. There's one more thing I need to show you, which is what to do about windows, because we haven't discussed windows yet. Let me do that as well. And then we can finish up for this section. Here we go. So this is my second run. So I'll just call this, rename that. So this is my insulated roof and 0, 1. Okay. So what I'll do is I will pick up both these files. So that's my uninsulated roof file. And then as soon as I pick that up, if I look over here under the hourly, you can see that's my base case. I will pick up one more ESO data set. So let me go navigate to the correct folder, which I think is DBA training SDI. Here we go. Here we are. Here's my insulated roof. And what I'll do is I'll simply plot the operative temperature, the equivalent temperature that Mansi was talking about for, let's say, the top floor, because that's the one that'll have the biggest impact. So the living room on the top floor, I'll just plot the equivalent temperatures for both of those rooms. So if I pull this thing down, I'm looking for zone mean temperatures. Can you see here? I have 3 sets of temperatures: air temperature, radiant temperature, and this operative temperature. So if I click on this operative temperature for the first floor living room area, and I plot it for both runs, right? So I'm clicking on this icon here. So you can see that. And just to give us a bit of, what shall I say, reference, let me find the outside temperature. So site outdoor air temperature, and I will plot that as well. Okay. So let's pick a hot day. So the hottest day is around here. So I'm going to pick these 2 days up over here, and now you can see what's going on. Okay. So on the hottest day, okay, so the outside temperature got to 32 degrees, 32.13, you can see here. And the operative temperature inside the uninsulated room was 32.6, so slightly higher than the maximum outside temperature. So you're feeling even hotter than outside. But when I put insulation on the top of the roof, above the concrete slab, because then the slab acts like a moderating influence, you can see here it's come down to 29.3. So I got 3 degrees depression by doing this one energy efficiency initiative. So you can work on other things as well. Okay. And of course, you can look at how it's doing across the month and you can examine it and so on. You can take these numbers to a spreadsheet. So it will save it as a CSV file with a timestamp and just these 3 variables. You can work on it and so on. So hopefully that's given you an idea of how to do constructions and what to do with them. Now, I want to do windows before we kind of take a break, but one of the things I'll quickly show you before I leave this is that if you go to this data visualization tab, as long as you set up, and what I'll do is this is March. So what I'll say is that I want it to be for the interval that I wanted to plot for is the whole run period. So we ran it from 1st to 31st of March. So for the entire run period, it's giving me, this is external sunlit fraction, external surfaces. What I want is the solar incident on the outside. So here is my solar incident radiation. Now to do this, before you make the simulation run, you must switch on the surface variables, okay? Hopefully I can show you that as well. And then it will plot all these things for you and you can take pictures and compare. If you set up the scale by switching on this, you can then give a fixed scale. And if you do that, then when you do two comparative runs, you can show the same on the same scale, so the colors will look correct. Yeah, you can make out whether it's improved the situation or not. So there's many tools within DesignBuilder that you can adjust for that. Okay, so let me just go to Windows and then we'll show you what to do with Windows. So Windows are then, you can provide the information on Windows from the openings tab. Again, you can either put it at building level, or you might want to put it at block level, or you might say all the west facing windows are something, the north facing windows are something, whatever. You can set it up, okay? But what you are interested in putting is the operational or the performance parameters for Windows. And those performance parameters can be adjusted under what's called glazing type. Okay. Now, I don't know if I covered this last time, but this was one of the slides that we talked about in the energy simulation introduction. So for Windows, the things that are important are solar heat gain coefficient, when you are looking at the impact of solar energy coming through the windows. Visible daylight, sometimes called VLT or TVIS, depending on the manufacturer, which says what's the percentage of daylight that comes in. And then the U value, which is the overall thermal transmittance of the window. Okay. The thing to be careful about, as I said last time, was that you get values for center of glass. Most glass manufacturers will only give you that. What you really want is the whole window performance. Okay. If you have these three numbers, then you can describe that performance. And DesignBuilder, I should say Energy Plus, actually has got models within it. Looking at that combination, it will pick the correct model, maybe a low E model, maybe a reflective glazing model, an absorptive glazing model, whatever. And it will work out the angle of incidence modifier. So as the sun keeps changing every hour, it will work out how much is transmitted, how much is reflected, and how much is absorbed. Whatever is absorbed, it will either re-radiate back into the room, or the wind on the outside will strip that heat off. Okay, so it's doing this enormous calculation every hour of the day. So the picture on the left is a dark glass. Visible light transmittance is very low, 14%, but it's the one on the right is 55%. But you can see in terms of the solar heat gain, they're approximately the same. The same, about 54% on the left, 55% on the right. So how do you put that into DesignBuilder? So if you pick this, and I've got a model right now, which is a clear single glazing. And if I examine that, right, you will find that I can change the way that this is described. Okay, right now I've got generic 4mm glass. And if I calculate the U value for that, from that glass, it will go to the spectral data file, and it does quite a complex kind of calculation, and it gives you the U value, the solar heat gain coefficient, and the light, visible light transmission, right? However, if I don't want to do that, I can just say simple And then I can give it those three values that we were talking about. Okay. So you can see that I've got a few different options. I'll show you one where I've changed it. Now, if you leave it on materials, which you can if you want to, right? You will find that there are a huge number of glazing products already built into DesignBuilder, okay? And that's really the international glazing database that has been programmed into DesignBuilder. So if I bring this here, here we go. You'll find that there are 3 libraries. Oh, now there's more. So there's absorptive, there's clear glass, there's coated glass. So if you pick them, you will find that there are products from most of the manufacturers in the world. Now, I know you've got Asahi glass, Guardian glass. These are all available to you if you know your product, okay? But the thing to remember is that even when you combine, and if you put, say, more than 1 layer, if you put 2 layers, you can then change the layers in between here, right? So you can have 2 pieces of different kinds of glass. You can have air or argon or krypton. These are noble gases which, you know, reduce the U value across the window. But certainly if you do that, then you have to account for a frame U value separately. Okay, so instead, what I suggest to you is that you may be probably better off taking a combined whole window performance number and putting it here. Obviously, it's up to you to do whichever you prefer. But if you do simple, which I've done, then just make sure that you remove any framing because you've already considered the framing in the U value and the solar heat gain coefficient and the visible light transmission. Okay, so that will do that. Now, what I'll do is I'll show you another one which I set up, which is that I picked up, or we developed a double glaze system when we were running the course with the SEP guys. So you can see what I've done here. There is a change in those numbers. Okay. Now you need to be aware of what these numbers mean. So if you have a solar heat gain coefficient, that tells you how much solar radiation that's hitting the glass perpendicular is going to come through the glass. Okay, and then for every hour, the model will adjust how much of that actually enters because there's the higher the angle is, the higher the reflectance is. Okay. Then the light transmission obviously is daylight, but the U value is quite impacted by whether you have 1 piece of glass or 2 pieces of glass. Okay. Now U value is total thermal transmittance. Okay. So basically it says that if your transmittance is high, then if for every degree temperature differential across the glass or the window, then your heat transmittance is faster. So if you have a lower U value, then depending on the delta T across that, the heat transfer is slower. Okay. So in some situations, you want it to have a lower heat loss. In some situations, you may want, that may not be that important. I won't say that it doesn't matter, but might be less important. Okay. So in cold countries, when there's a really big temperature differential between the inside and the outside, if you're in, say, Sweden, and it's the middle of winter and it's night, it's minus 20 degrees outside, and you're struggling to keep your inside at plus 20, that's a 40-degree temperature differential. That's a huge driving potential for heat. Okay. If you're in many parts of India and the temperatures are sort of 20, 25 most of the time, and you want to keep it around there, well then, the heat transfer through this component may not be that important. It may be much more important for you to shade it or to look at the solar heat gain coefficient, which is how much solar radiation is coming through that window. So you need to kind of think about, okay, is this building only occupied in the day? Is it occupied 24 hours? In that case, what should my window be doing? What kind of shading should I be providing? That sort of thing, okay? So with this, hopefully I have answered all the window construction and windows and construction questions. The window and the roof window or a skylight is exactly the same. You just need to give it the same numbers and you can draw it on the roof and it will account for that. I think that's good enough, Amanda. We might take some questions and then we might take a quick break and come back for the second session.
So let's take a few questions and then, yeah, we'll take a break. So, right. So first question is, I would like, okay, the layers that we add in the building envelope, how it provides or calculate, how is it provided and calculated data of a space if windows, doors, weathering strips, loses, or infiltration in building?
Okay, thank you for that question. So there was something there which I didn't show you, which has come up on this question. So I will show you that. Let me just share my screen again. So the one question that I had not answered, which came up there, was infiltration. Okay, infiltration is air leakage, right? And typically it's quite difficult to try to predict what is the air leakage. And usually we do that by putting a blower door test and testing out a bunch of houses or schools or whatever, and coming to some idea of how much the leakage is. And then depending on your construction, you try to either make it tight by trying to reduce the gaps where the windows are fitted. And in wooden construction, you're looking at the gap between the wall and the floor and between the wall and the ceiling. In concrete construction, that's not a problem. You have very, very tight gaps when you've got a concrete floor and a concrete wall. There's nowhere for the air to go. But then your gaps are all the gaps around the windows, around the doors, underneath the doors. Those are the areas where you have gaps. Now you can model them. As you can see on my screen, at the bottom of the construction, there is an infiltration requirement, okay? Now this crack template, it only comes on when I ask it to calculate natural ventilation. Okay, so if I have natural ventilation, it will ask me to select a template for, is the construction tight or is it poor or very poor? So typically, in India, I would say that construction is fairly leaky, so you might want to put a poor construction. If you don't know anything better, leave it at 1. 1 is equal to atmospheric rate. Basically, it means that at atmospheric pressure, every hour, the whole of the air volume leaks in a space, okay? Now, if you were going to do this, if you had some idea of what the leakage rate was because you do a blower door test, if you look up, say, passive house is a rating scheme, which I'm sure you've seen. They do a blower door test in what's called an N50, okay? So within DesignBuilder, you can actually change the way the infiltration units are described. And there are a number of ways of putting these units. You can say, I want to do it as per N50, which is the blower door test outcome. And if you then change that, it will change the infiltration rate based on that. So now you can say, okay, I did a blower door test and my house only leaks at 10 air changes per hour at 50 pascals. You can put that number in, okay? So if you have test data or you have some research on test data, do that. If you don't have any, leave it at 1 air change per hour or the default, which is 25 air changes per hour at 50 pascals, okay? Hopefully I've answered that question. The other part of your question, I thought I've already answered, which is all those layers and how to calculate U values and so on. Okay.
Thank you, PC. We'll take next question. If we provide AAC blocks with insulation, we can control the heat gain from outside. But how do we control the heat produced inside a building? Because AAC block and insulation helps by not letting the outside heat penetrate inside, and vice versa for inside, without using the air conditioning and ventilation. So how do we control the inside heat?
Well, anonymous attendee, that is a very insightful question, and thank you very much for that. That's up to you as a designer, right? So if your building is what we call fabric dominated, that means it's the building envelope that plays a bigger part. But if it's what we call an internal load dominated, then it's completely different. If you go to a data center, for example, a data center is full of computers producing lots of heat, huge amounts of heat. You actually don't even need a building. You just need a very thin skin around it. And the heat is trying to get out. Your air conditioning system is desperately trying to cool the space because there's so much heat being generated. Okay. So yes, you have to kind of balance between, what's the climate outside? What is this building being used for? Those are ideas that you have to discuss amongst yourself and say, should I really insulate this wall a lot or should I not? Okay, and these are the questions that you have to think about. Very good question. Thank you very much.
Yeah, and if you go through your SLMs, your heat transfer module, passive design, and natural ventilation, you will get more answer to this on, how to passively design your buildings to avoid this, in terms of, externally dominated building and internal dominated building. You can work on, in terms of internal dominated, you can work on, how to reduce heat generated from the equipment, from lighting, etc. And you can also work passively, how to like for example, night cooling, how to do it, so etc. So please do go back and refer the SLMs of these 3 modules, and maybe you'll get more answer to this. Okay, so next question we have is how to account the impact of window frame for glass properties.
Okay. Now, that is not something that I can cover in this module, okay, because I will just show you. There are specialists who will. Can you still see my screen?
Yes.
Okay. Yeah. So, so there are specialists, people and programs who do only this. In fact. There's also a problem that, residential windows come in fixed sizes. So you can work out for a residential product, what is the overall U value and solar heat gain coefficient, etc. But when you're doing a curtain wall for a commercial building, every single design is bespoke. It's a custom design for each building. And typically, the glazing supplier, the glazing contractor in Australia, is asked to provide a therm analysis where he finds out what is the frame performance, and then he combines it with the glass or the double glazing system that he's been asked to use, and then it'll give him a combined curtain wall performance, and that'll come out as exactly these 3 values: U value, solar heat gain coefficient, and visible light transmission. Now, my suggestion is, because you are doing the design, you might want to talk to some glazing suppliers, your Ashahis and all these other people, and then find out what is the range of U values that they can provide for the whole window, and then try and keep your U values in that range. Now, solar heat gain coefficient, for the whole window is less difficult. You can find the fraction of the whole window, which is the frame fraction. So typically the frame area will be, somewhere between 5% to 15%, unless it's a very residential thick frame type window, but you can work that percentage out. You know the solar heat gain coefficient of the glass, solar heat gain coefficient of the frame, you can kind of assume it to be almost zero. It's not, it's a little bit more than zero, but just near zero is okay. And you can take a area weighted average to find what the solar heat gain coefficient is for the system. The U value is a little bit more complicated, but as long as you've got a range that you know you can stick to, then you can make sure that your design is practical. You can't get very low U values in glazing. It's not like opaque walls or roofs where you can get very low U values. Typically a double glazing, even with a good quality frame, will be in the low twos. And if it's a poor quality frame, your glass might be 1.6 or 1.8, but the whole window's performance will be significantly derated if you've got a thick metal frame. It may be 2.5, it may be 3. If you've got single glass and metal frames, then it has to be 5.8 or 6 or more. Now, just be aware that these models actually don't calculate correctly the performance of any window where the U value is greater than, I think it's about 5.8 or 6 or something like that. And that's because of the same thing as ground heat transfer. You are squeezing three-dimensional heat transfer into a one-dimensional equation. And the limit of that one-dimensional equation comes around that 5.8 or 6 U value. So it won't give you any more disbenefit if you have a U value of 7. Okay, so just be aware of that. My colleague, Dr. Peter Lyons and Dr. Charlie Churcher at Lawrence Berkeley National Lab have actually written a paper on how to adjust this. Energy Plus is not in any hurry to change that because, in the US, you cannot buy single glazing for residential houses. You can only buy double glazing. Single glazing is more expensive than double glazing because it's a special order. Okay, so hopefully they'll come for us for developing countries sooner, but right now it doesn't look like it's going to happen.
Okay, thanks, PC. So let's take 5 minutes break and then we'll come back for the next.
Sounds good. 6:08. If everybody is back at 6:13 or 6:14, we can start. Oh, that's my time. Sorry.
Yeah, right. So
what's your time?
It's 12:42 now. So we'll come back at 12:47. Yeah.
Okay, perfect. Thank you all.
Right. Yeah. PC, it's 12:47 now. I think we can continue.
Okay.
Also, we are slightly running over time, so if possible, yeah.
How many minutes do we have?
So we have till 1:15, which is another 30 minutes.
30 minutes. Okay. All right. Let's see how we go. Okay. You can still see my screen, isn't it?
Yes.
Okay. So what I wanted to cover was now some of the things that actually Mansi has covered in today's earlier lecture, which was really quite well prefaced for my design builder workshop. See, for a building, we need to kind of understand what is it that we are looking to do when we do this analysis, right? If you remember that model that I keep talking to you about, we have covered this section of the model. So the geometry, the windows, the frames. So now we're going to look at this thing called loads. Okay, so what is that? Well, the question to ask is, why do we do air conditioning or natural ventilation, right? And the answer is that because there is some heat being either gained or lost from a space. And because of that heat gain or heat loss, the space becomes uncomfortably cold or becomes uncomfortably hot. So we have to either make it colder by doing air conditioning or make it warmer by adding heat, right? These things are called loads. So the 4 loads that air conditioning engineers talk about mainly, and now passive design people and building designers we all use the same language, and that is, one is shortwave solar radiation that comes through the transparent part of the window. We've already covered that and how it is modified by the kind of window that you got. But this solar radiation comes through the window, it hits something. So it could be the floor, it could be you, could be the table, chair, whatever. And then that's converted into long wave radiation, infrared radiation, okay? Infrared radiation is opaque to glass, so it doesn't go out as quickly as it came in. So that's the reason why if you have a room which has got a large piece of glass and the glass is facing either south or east or west in India, it's getting solar radiation that's coming in and it's heating up the place, but it can't get out as fast. So you need to think about that. The second source is what we are going to be looking at now. What are the activities within the building that are causing temperature change? And we will talk about 3. We will talk about people, occupants. We will talk about lighting, and we will talk about equipment. Okay. The third thing we have already discussed is this temperature differential, and that is what the U value of the materials do. So if you have a high temperature differential, then the U value becomes important. If you have a low temperature differential, then the U value is less important. And that's in opposite to the solar radiation. If there's a lot of solar radiation, right, and then it will depend on what is the outside temperature and solar radiation combination for you to decide where you want to concentrate your efforts. And the last one is infiltration and ventilation. Again, infiltration is air leakage that you don't want. Ventilation is what you want. So if you're doing particularly if you're doing air conditioning, then by law, there's a minimum amount of outside air that you must deliver in most countries, so that you can keep the air from becoming polluted. You want to reduce CO2 levels, you want to make sure there's oxygen in the air, all that kind of stuff. So we're going to look at this internal heat generation, and we are going to look at the ventilation that you are going to provide. Okay, these are called internal loads. And you need to tell the model that. So the way you tell the model that is, you tell the model what is the maximum design condition, the maximum design load. And then you tell the model, okay, how does it vary during the day or the week or the month or the year? Okay, if the model doesn't know these two things, it doesn't know how to account for the heat gain or heat loss from these things, right? So it will depend on, typically these things will depend on National Building Code or ECBC or LEED, or all these other green building rating schemes will give you typical values that they expect you to use if you are going to have your building rated with using these systems. So let's go ahead and work through it in DesignBuilder. Now in DesignBuilder, everything you want for these things is in these two tabs, the activity tab, which is over here, and the lighting tab, which is over there. Okay, so let us go through it one by one. So in the lighting tab, you talk about mainly a lot about what the people load is. What is the occupant load, right? So you can see here, there is a template here which says domestic lounge, which I've applied across the whole building, but I have changed the template for the bedroom. Okay, and I don't think I've changed it much for the kitchen. Oh yeah, for the kitchen as well, I have changed it, right? But let me say that I put this default template across for the whole building at building level. So the first question I need to say is this zone occupied or not occupied? Is this zone going to be included in the thermal calculations? And pretty much all the zones in the model should be included in the thermal calculation. Whether they are air conditioned, not air conditioned, doesn't matter, but you must include them in the thermal calculation. You may not use it in the daylight calculations. If you have a garage, you really don't want to know what the daylighting is in the garage. You can untick it, so it won't do any daylighting calculations in the garage, right? So once you tell it that it's occupied, then you need to give it, in this case, I've asked for it in terms of a number of people, okay? How many people in that zone? So I have put here 10 people in the living room. That's my maximum design occupancy for that zone, right? Now, the question is, how do these people, or how does through the day, how does this criteria change? Is it going to be 10 people all the time, or is it going to actually vary? And we give that by giving a schedule or a profile, okay? Now I'll come back to profiles because I want to go through all the loads, and then I'll come back to profiles, because for everything we need to provide a profile. Now, the second thing we need to tell it is that how much heat does a person produce, okay? And that depends again on the standards and codes that you are applying in different countries. Now, where I do, and you'll probably find that either in the National Building Code of India or in the ISHRI documentation. The air conditioning guys are the ones who are most interested in this, because they design all their air conditioning systems by assuming some level of heat from a person. Okay, so the activity here is eating and drinking. So if I examine that, you will see that I've got, I believe, here we are, 110 watts per person. Okay. Now, typically in Australia, if it's an office situation, we would use 130 watts for a full, for one adult male, and maybe slightly lower for an adult lady, and even slightly lower for a child, okay? And that's why you can see here that there is a factor here for if you have an average of men, women, and children, what should be the factor? So typically we put it at 90%. So 90% of what a full adult male generates as heat will be included in the energy simulation. There's a CO2 generation rate. If you're going to use CO2 control, then it looks at that. That's for air conditioning. Okay. Now, one thing that you have not seen here is how much of this 110 watts is latent load. How much of it is sensible load? How much of it is latent load? How much of this is moisture load is latent load? Now, if you don't specify anything, Energy Plus is smart. It sort of says, okay, what's the total? And then depending on the temperatures on the inside and the outside and the relative humidity, it will work out what's the latent amount. Now, I would say that for residential calculations, that's enough. You don't really need to go any further than that. Energy Plus has got a really smart subroutine to do that. However, if you're doing an air-conditioned building, air conditioning engineers like us are very conservative. We want to know how much is the latent load. So what we do then is that we need to actually tell the model of that 110 watts, how much of that is sensible, how much of that is latent. Okay, typically it's around 60-40, but again, you will find some numbers in ISRI, in ECBC, in NBC, somewhere you'll find those numbers. But what you do is that you go to the same model options that we did the settings for. And if you want to fix the amount of latent load, then what you do is that you can change the occupancy latent gains from dynamic to fixed. And when you do that, you will find that you'll get an extra line in here which says, okay, what's the latent fraction? So from your 110 watts, you can tell it what the latent fraction is. I've got a default here of 50%, which tells me that 55 watts is sensible and 55 watts is latent. Now that's not always appropriate, so you will need to find what's happening. In Australia, we typically use about 42% as being the latent fraction. Okay, as I said, if you're doing residential, this is not, and not air conditioned, this is not something you need to worry about. So I'm going to go back and set it back to dynamic. Okay, let me do that. Now, the next thing that you need to worry about is if you're doing any sort of comfort calculations, say a predicted mean vote or a percentage of people dissatisfied, then you may need to choose a clothing level for what people are wearing. You only need to do that if you're doing thermal comfort analysis. If you're not doing a thermal comfort analysis, not required. If you're doing a comfort analysis, you will also, and if you have a lot of glass on your facade, then you might need to change this to a surface with the largest window. What it does is it's looking at the view factor from the middle of the zone to all the different surfaces and then working out the radiant temperature. If you have a big piece of glass, that surface temperature will dominate the calculations. So you need to tell it that. Okay. Now, air velocity, typically you don't need to touch it. Okay. Particularly if you're doing air-conditioned buildings and you're doing the PME calculations. It only is useful if you're doing thermal comfort calculations. But if you've got a ceiling fan and you want to do a thermal comfort analysis, then you may need to change the velocity for calculations. Typically, we leave it at 0.13, 0.14 meters per second. You can barely feel the air. But as I said, if you've got a ceiling fan, you've got to make some changes for that. These other bits are not so important. You come down to what is the heating and cooling set point. Now, that is only important when you're doing air-conditioned buildings. You say, what are you going to heat to and what are you going to cool to? So you're deciding what is the thermostat setting for heating and cooling. Again, Setback temperatures are not important for you if you are explicitly switching off the air conditioning system and switching it back on. The only time that it's really useful is that, if you like, again, if you're in a really cold climate and the outside is very cold, -20, that kind of thing. If you switch off the heating system at night when people go away back home, then the building gets really cold. And then the next morning, it's very hard to bring it back up to temperature. So what they do in places like Sweden, they don't switch off the heating system. It runs 24/7. Only thing is, once people have left the building, it allows it to not from 25, it drops it to the setback temperature, as we call it. And so in this case, I put 12. So it'll drop down to 12 degrees, but it will hold it at 12 degrees overnight. So when people start coming back in the morning, it's very easy to get it up to speed quickly. Okay. But for our purposes, the 21 and the 25 are the important ones. If your air conditioning system has got some active humidity control, you can put the range. If you don't have any active humidity control, DX systems, you can't actually do, unitary systems, the split systems that you use in most places, Daikin, Mitsubishi, etc. You can't really control humidity. Don't worry about it. Okay. Make sure both of these are switched off. Okay, and that's a very British kind of control. We don't use it very much at all. This one is important, the minimum fresh air. That is the outside air that an air conditioning engineer talks about. Okay, so if you had seen my previous chart, this one here, let me go forward a bit, hang on. You can see that there is this word here called outside air. Okay, or fresh air. Now in Delhi, the air is not fresh outside, so it's better to call it outside air, right? So when you talk about the loads from people, you have the heat that is generated by the people, but you have to bring in outside air so that the oxygen levels, CO2 levels, all that stuff is taken care of. When you bring in that air with a ventilation fan, that brings both temperature and humidity into the space, and the air conditioning system needs to deal with that. That's why you need to provide that input to the model, which is what you're doing here. Now, there are two ways of providing input. One is a liters per second per person, and then there is a mechanical ventilation per area, so liters per second per meter squared. Now, if you put numbers into both these boxes, it will add the two together. If you put numbers into one box and call the other one 0, it will use only the one that it knows about. Okay. Now, there is a lighting thing here, but the lighting thing here is only what is the target illumination that your lighting system is going to target. And when you do daylighting calculations, it's going to look for this level. Okay. This is probably a bit low. I'd probably have it around 250 lux. But again, you may need to look at your codes and standards to give what is correct. Now, typically, we are providing what is the lighting system's output. And when we do a lighting system output under the lighting tab, we are saying this is the main lighting system. But if you go into, say, a jewelry store or a watch display store, or even a sari display store, if you wish, there will be some lighting that is not the main lighting, but that's feature lighting for your product sales. And that's considered to be a separate lighting system, and you need to provide what is the lighting density for that. Okay. And typically, you don't need to worry about that. After this, you'll find that there are 5 ways that you can give other heating systems. So either you can say computers or office or miscellaneous or catering or process or any combinations of the 2 of the 5, right? Typically, we will leave only 1. And in this case, I've called it office equipment. I put it 3.9, about 4 watts a meter squared. You can take the whole area of the house and you know how many watts is being used or as the maximum demand for that kind of thing. And that can include things like TVs and stereos and whatever else that you might be using. Now, the only one that I would point you to is that this catering load is useful because unlike the other loads, it actually gives you this thing called a latent fraction, a humid load. So if you are cooking, so you're cooking rice, okay, there's a lot of steam. That's a humid load. That's increasing the temperature and the humidity within the space. If you have to condition that space, you need to consider that. If you're in a restaurant, you're being served meals, and the meals have got a lot, hot meals. There's a lot of latent load coming from that. So you need to then switch on a catering load. But otherwise, you're typically, they're all sensible loads, okay? So that's one set of internal loads that you need to think about, and that is for people, okay? So sensible and latent loads from people, outside air impact on people, equipment load is the other one. For lighting, you need to go to the lighting tab, and then you need to say what is your lighting power density, okay? And I know in the ECBC, there's a lot of effort on the lighting. Typically in an office, you may be down to 6 watts or even less. In Australia, we're down to 4.5 watts. The lower the lighting load, the better it is for the building, because whatever the electricity you feed into a lighting system finally comes out as heat, and that heat needs to be accounted for by the air conditioning system, right? So if you generate less heat in the space from lighting, the less your air conditioning load is. Okay, so that's all the internal loads here. Now we haven't talked about schedules, and I want to talk about that now, okay? So typically, if you look at what is provided in different standards, okay, so here's my standard from Australia, and hang on a minute, I've actually got the standard from the, yeah, here we go. So this is ECBC, okay? So in the ECBC, table 912, schedules for business office building. Let me make it a little bit larger so you can see that. Maybe, yeah, okay. So it's telling me, here's a schedule for air conditioning and the fan. When is it on? When is it off? And here's a schedule for a daytime office building and a 24-hour business. Okay, 24-hour business, obviously it's open all 24 hours it's on. For the daytime, it's giving you a number. So till 7 o'clock it's off. From 7 to 8 it starts, so they've given it a 1. And then it goes all the way to 21 to 22. So 10 p.m. it switches off. Okay. Then there are other schedules as well. So if I in fact showed you if I took it back to where my National Construction Code of Australia was, for offices, I have a schedule which works from Monday to Friday. There's a schedule for people, occupancy. And what it's telling me is that till 7 a.m., there's no occupancy in this office. From 7 to 8, there's 10% of the design occupancy there, okay? And then by 9 o'clock, it gets to 70% of the design occupancy, and it stays at 70% till 5 o'clock in the evening, and then it starts to reduce. And by 9 p.m., again, everybody's gone home and 0. And in a similar way, it's giving me for lighting, it's giving me for equipment, and you already saw air conditioning, okay? And the same thing is repeated for Saturdays and Sundays and public holidays, which are quite a different way of doing it. So if you plot this, then it will look something like that. Now you need to tell DesignBuilder this information, okay? Now, there are a couple of ways of doing it in DesignBuilder, but I'm going to show you the complicated way. okay? And why I'm showing you the complicated way is that if you understand how to do the complicated way, then you can do it for the simpler way. It's much more powerful compared to a simple way. So there is a language within DesignBuilder which is called an IDF, Input Data File Language. Okay, it's very text-based. If you know any, Ruby, Python, Pascal, C++, C#, whatever, it's very simple. So it's an object-oriented type program. And so I'm going to show you this lighting load or this lighting schedule. So what it's telling me, this is a very simple one. Let me see if I can get a bit more complicated one so I can show you. Let me pick something from activity. How does I have a feeling these may all be simple, but let me take the occupancy schedule. And let me see if I can find something that's a bit more complicated. Okay, let me pick one of these. So here's an occupation schedule that we developed. Okay, I'm just editing that, right? So the name of the schedule is this ABGR class 5 occupancy schedule. Class 5 in Australia just means office. So the name of this object is a schedule compact object. And there's a comma at the end. Okay. The name of the schedule is the same thing. I've just copied that and put it here. ABGR class 5 occupancy. The type of schedule is fraction. So any value between 0 and 1 is acceptable. Beyond 1, not acceptable. Okay, it will grumble. This schedule will go from January 1st to 31st December. So there is this through block that I'm writing. Okay, so this through block goes from here to here. Okay, now obviously this already should be starting to give you ideas. If you're doing a school, you have days when the schools are on holiday. You have, or rather months when the school might be on holiday. And you have other times when the school is in session. So you can write through blocks. So you can write a through block through 31st of March. So it will give one schedule till 31st of March. Then you can write another schedule through September the 30th. So from not 31st, but the 1st of April till the 30th of September, you can apply a second schedule. That's when it becomes powerful. As long as you go from January to December, this is a very powerful way of doing it. Okay, so there's my through block. Then there are some reserved words. So for weekdays, for a summer design day, for winter design day, this is my occupancy schedule. Okay, so from until 7 o'clock, 0. So from midnight to 7 a.m., there's no occupancy, 0 occupancy, right? From 8 o'clock, from 7 o'clock to 8 o'clock, 15%. From 8 o'clock to 9 o'clock, 60%. From 9 o'clock to 5 p.m., 100%. Okay, and so on. And you can see the format is very clear. There's colons, commas, and then after I finish the weekdays and the summer design day and the winter design day, I've given it for weekends. I've said holidays, and then one reserve term is all other days. So if I missed any day and it comes up in the simulation, then use this profile. Okay, and right at the end, there is a semicolon. Now, don't be worried. There is a lot of information available for you. If you click on the help part of it, it gives you a good set of examples. It gives you, see, the one you're looking for is compact schedules, and there's a whole listing on how you should do it with examples. Okay, so go and have a look at that. And if you learn how to do it, think about the ways where you might be able to use it. If you have external shades or internal shades or curtains, okay, you can actually provide one schedule for the whole year where you can say in summer, draw the curtains, in winter, open the curtains, in middle seasons, do whatever it is that you want. So from January to December, you can give a series of options. Okay, that's very powerful. I really suggest that you guys learn how to use that. And once you do that, when you start to do shading devices in openings, internal curtains, internal blinds, so in the shading openings tab, if you do window shading, in window shading, you can see you can choose blinds or curtains. You can put them on the inside or between panes or on the outside. You got a whole bunch of different ways to control these things. Okay, and you can decide how to control it, and then you can provide a schedule. Okay, so it's quite when you draw a component block that's representing a tree, and you want to make sure that in winter the leaves fall off, so then you can change the transmittance schedule of the component block, and that way you can adjust how much solar radiation is passing through the tree and reaching your window in the winter. So many options there. Let me just check here. Yes, I think I've covered pretty much of what I wanted to do. I think we can probably stop. One quick thing I forgot to show you under constructions, which I'll just cover, and then we can take questions. And that is that when we were doing that U-value calculation, let me pick that. Okay, there's an insulated roof. I wanted to pick that. And let me examine that. Okay, here's your thing. If I did the calculation for that, then I get a U value of 0.313. Okay, now in some codes like ECBC, LEED, all that, you have to create a reference model which has got some exact U value. How do you do that? There is actually in this screen, there is something called a set U value. And in this place, you can tell it what to aim for. So suppose I say that instead of 0.3, I want an exact U value of 0.4. Okay. Then what it will do is that as long as you have an insulation layer, it will modify the thickness of that insulation to give you exactly that U value. So if I say yes, what it's done is it's gone and changed the thickness of this XPS insulation layer, so that now if I calculate that, I'll get an exact U value of 0.4. That's useful when you're building reference models for rating systems like ECBC and LEED and all these other kinds of rating systems. Okay, I'm sorry, I forgot to show you that when I was doing it in the previous lesson. So I think that's good. Amanda, we can take some questions and then we can decide what you want to do next.
Sure, yeah. Okay, yeah, so now let's try to take up all the questions for PC and Mansi. I hope Mansi, you're still there, right?
Yep, I'm here.
Yeah, cool, yeah. So we have a question here. Is there a way to load EPW file which are not available in DesignBuilder? For example, in Nepal folder, there is no location to choose from, but there is an EPW file available for Nepal on Energy Plus website.
Yes, there is. If you read the Energy Plus, the DesignBuilder documentation, there's a way for you to set up a new location. So with that location, you can bring in your own EPW file and it will do the calcs. It's all there in the help file. Go and have a try. If you can't make it, maybe we can help you out, but it's all pretty easy. You just have to give it a couple of tries to get it across the line.
Yeah. So the next question is also regarding weather file. Does DesignBuilder provide weather conditions as per the condition?
Did you want to give us a little bit more in this question? I'm not quite sure what you were asking for. If you're asking for a design condition for air conditioning sizing, then yes, it does do that. So suppose I go to my location on the tree, right on the top there, and I click on the location tab. If you go right to the bottom, there is the summer design weather data, okay? And you have a number of options. Now, you have to talk to a mechanical engineer and he will understand all these things. Typically, we design to a probability. So we say that, you know, it's a 1% confidence level or a 2% confidence level or a 0.4 confidence level. That just means that we are basically looking at the previous 20, 30 years. We feel that this weather condition won't be exceeded more than 1% of the time. So you design an air conditioning system for that size. Okay. Now, you can see here, I've got 6 options, right? And I've selected a single design month, right? So I've got what are called dry bulb priorities. So it kind of looks at the temperature and then it says what is the coincident humidity at that time for design condition. If you're in Mumbai or in Trivandrum or a really humid place, then you need to actually design for the humid condition, in which case you will pick the wet bulb priority condition, where it will first look at the humidity condition and then give you a coincident air temperature at that humidity condition, right? Now, typically, we have gone away from doing 1 month because what happens is when you do a month, you're kind of guessing which month it's going to peak on. But really, if you've got a complex design, a lot of shading, different kinds of glass, different thermal mass, then the angle of the sun, the shading devices, what's happening inside the building can make the peak not necessarily in the summer months, but it could be in one of the other months. Okay, so what we do is we pick the multiple design month scenario, and ISRI has provided us data for India. So then you get, for every month of the year, you get a design date. So it cycles through all 12 months, and then it reports for each zone, where is it peaking? Okay, so it's quite complex, quite sophisticated, and you can do a lot of, if you know what you're doing, you can size your chiller block load, which is your diverse load. You can actually size air handling units. You can put different zones on one air handling unit, and it will size the air handling coil. You need to know what you're doing, but you can do that. And you can also size the zone level equipment. So VAV boxes, active chill beams, fan coil units, you can do all of that. And then, you know, it's a little bit involved, and you should probably talk to a mech engineer who can kind of understand what's going on. But that's all possible within DesignBuilder. And also, probably in about a month, we are releasing a beta plugin for reporting this in the way a mechanical engineer can easily use it. So if that becomes available, I'll make sure that the Solar Decathlon team has got access to that plugin. You have to use DesignBuilder version at least 107, I think it is, or 106. This is what I'm using now, but it will allow you to do that plugin then. Okay, so I hope that was what you were asking me. I'm not sure, but I'm trying to anticipate what your question is.
So adding more to the regarding the weather file. So the weather file that Design Builder is using is the TMY file, which is the typical meteorological year file. So you can also actually use AMY file, which is the actual meteorological year data. So this you can get data if you have weather station to your nearest location and you have data from there. You can use them directly by converting them into EPW file and then importing in Design Builder. So yeah, so there's one of the option where you can get the nearest weather conditions as per your location.
Okay, so just to add to that, EPW is only a format.
Right.
Okay, you have reference weather files which are calculated by looking at 10 years worth of data, but there's a TMY format, an AMY format, an the IWEC format, and there's many other formats. They are done by academics. They write research papers on this and they say this is good for that, that is good for that. EPW just takes that data and puts it into one text format, which then the simulation engine can read. And because there are so many EPW files in the world, every energy simulation engine is now using EPW as a format. So IES will read an EPW format and convert it. TAS will do that. IDA ICE will do that. So it pretty much DRINSYS will do that. Everyone will do that now. Hopefully that's sufficient explanation. Yeah, go ahead.
Yeah, so we'll move on to the next question. So probably this question is for Mansi. So in Mansi's presentation, the surface temperature is much lower in outer insulation than inner insulation. So does that mean outer insulation would always be a preferable choice, or does that depend on weather conditions or location?
Interesting question. So as I have already mentioned, that location of placing the insulation is very much dependent on how the building is. Is it naturally ventilated building? Is it air conditioned building? Is it operated 8 hours a day, 24 hours a day, where it is cool 24 hours a day? So all of the, and definitely the weather. So say I would give you a simple example. So it is not, it is very much conditional where you actually provide your insulation. Say for if in a cold climate, you want to retain the heat gained from the glazing, right? Then you have to provide the insulation on the inner side probably. Say in a hotter climate, you want to stop the heat coming inside right at the beginning. So then you, during that time, you provide your insulation probably on the outer side. So it is very much dependent on the weather and every other detail like conditioning and other things.
That's very good.
Yeah.
Yeah, thank you, Mansi. And you can test this using Design Builder.
Correct.
So, the only thing that I might add is that you can think about thermal mass being a battery, right? So what Mansi just said is, if you're in a hot climate, what do you want to do? You want the thermal mass to not get charged by the sun. So if you put insulation on the outside, you stop the heat on the outside and the thermal mass stays cool. The effective temperature, the operative temperature will be lower. Okay. So if you're in a cold climate, you really don't want the mass to get really cold. I mean, if you're living in a flat in Delhi, by the end of winter, it's freezing because every wall is now 18 degrees centigrade or 15 degrees centigrade or whatever. In that case, it may be, as Mansi said, better to use the insulation on the inside because the thermal mass you keep outside and the insulation keeps it, if you put heat into the room, it doesn't get sucked up by the whole of the thermal mass. And you can test that using Design Builder. Okay.
Right.
Thank you,
So next question. What if we are deciding to give a cavity wall? It looks like an incomplete question, but this was regarding Mansi's presentation.
Okay.
So I think this question came up when you were showing various wall types and
Correct.
with different U values. So
Okay.
his question is, what if we decide to give cavity walls? So what does, maybe he's talking about what thermal performance results like.
Okay, then probably we'll have to simulate. So there are two kind of cavity walls. One are aerated one and one are the closed ones. So this will very much depend on the, so U value, when you are calculating the U value, you can account for that open or closed cavity. And based on that, I think you can simulate in Design Builder and check how well it is performing as compared to the insulation.
Mansi?
Yeah, and I guess within Design Builder, you just model the layers. So you can have an air layer if there is a cavity. And depending on whether that is a vented air layer or a still air layer, you need to pick the right R value. Okay, that's the thing to watch out for. Mansi, are you aware if in any of the standards in India, there is some listing of all the different kinds of air cavities and what the R values are? I have something in Australia in our code, but I don't know of anything in India where that kind of listing is provided. But anyway, I'm sure you'll find, the students will find some data.
I don't believe there are some sort of calculations, or I think students can refer to the CARBS report. They have some sort of R value calculation with the cavity walls. So,
okay. I can, if people have difficulty finding that, I can send a table that we are using in our code, where we actually have got a listing of, whether it's a vertical cavity, whether it's vented, whether there's a reflective foil on one side. I think there's a whole bunch of cavities for which we have been using those numbers. So if you let me know, then I can give it to Amanda, and Amanda, you can circulate.
In fact, the students can also use the U value calculator tool provided by CARBS. So if you go to the CARBS website, they have, you can actually calculate the U value for various wall type, and put in your thickness, which material, etc. Yeah.
That's a much better idea. Thank you.
Then, so next question we have is there any calculation for heat island effect in Design Builder?
Ooh, it's a difficult question. I would say that Design Builder and energy simulation models are typically built for one building at a time. Heat island is about many buildings, and it's more about the albedo effect. So by planting, you can change the albedo. By having lighter color roofs, you can change the albedo. Having darker color roofs will increase the heat island. Probably not the best tool to use for, like a big layout level heat island effect. Mansi, would you agree, or do you have any? Yeah,
I agree. So, however, it would be very difficult for energy simulation software to do this. However, I believe NVMet can do this for you, calculation. Other software options can be NVMet. And I believe there are tools and plugins for Grasshopper which would help us into this.
Thank you, Mansi. We have last two more questions. So how would you select, how did you select to put 40 mm insulation, and why not other values is question for Mansi, I think. Yeah.
So what happens is, as you can see, so I calculated, so what we did was we did studies from we went from U value of 2.2 and went to up to 0.2 watt per square meter. and check the annual cooling load. Correct. So what we observed was that when we go from 2.2 U value to 1.4 U value, there was reduction in approximately 12.6% in annual cooling load. Again, when we went from 1.4 to 0.8, there was 13% reduction. When we again went from say 1.4 to 0.4, that reduction was 13.4, and 0.4 to 0.2, the reduction in annual cooling load was up to almost 2%. So there was not a significant increase in terms of a significant reduction in terms of annual cooling load. However, the cost of insulation would triple down. Say for a U value of wall to 0.4, with brick, you will require approximately 40 to 40 mm of insulation. But however, to achieve this U value of 0.2, with brick, you would require roughly around 125 mm of insulation. So that would triple down the cost. And it is when we do the calculation, when we check the cost calculation, it was not fitting. So the EOI was increasing quite a bit. So hence 0.4 was selected, I would say.
Right. Thank you, Mansi. We'll take up another question. Does the simulation tool suggest the shading solution? Which tool can be used to get shading requirements?
Very nice question. I think the only tool that used to be able to do it used to be Ecotech.
Yes.
I think now, does Grasshopper have some way of doing that?
Definitely, Grasshopper does have a plugin called Ladybug and Honeybee, which would help us to do the insolation analysis as well as to calculate the angle which we would require for shading. There are
so it doesn't really,
definitions. There is that possibility.
So within DesignBuilder, you can test all the shading devices you want. That is quite easy to do. I think I showed it in the last geometry session. So please do go and have a look at that. But within the openings tab, you can select a glazing type, glazing layout. So, and then you can build your own glazing layout. But once you've got the glazing, if you then select what is called local shading, you can then put a combination of louvers, overhangs, and fins on these windows. So with that, you don't actually have to physically draw these geometries, but you can, by using dimensions, you can put any combination of these values. So for example, you might say, okay, I want louvers and I want a fin on the left side and I want an overhang. So by just switching on these things, you can switch them on or off, then you can control the number of blades and how far they are from the window and what is the spacing, what is the angle, all that you can do. It's quite powerful. It came from, these guys at the Department of Energy in the US, they've been building energy simulation tools for like 40, 60 years now, I think. So these are all, they've been making it easier and easier for people to do that. So it's really simple to do. So between the templates that you can choose within DesignBuilder for the glazing layouts, which again, you can build your own. Sorry, that's not a glazing layout, that's a glazing type. But within the glazing templates, you can pick something, you can customize it a little bit. So you can get a whole series of windows and then you use the local shading tool, and then for each window you can put. So you can put it on each wall. You can go and put all the windows on that wall to have a particular kind of treatment, and you can change that for the east walls, the west walls, whatever. And even better, once you've done that, you can actually use the visualize tool to see that. See, I've applied it on the ground floor now by just clicking that on. So you can see how it looks, and you can see the solar penetration, and you can see what the impact is on that. And also when you use this model data tool, if you make sure that you give the different glazing types a different name and a different color, then very quickly you can visualize whether you put the correct glazing on the correct, orientation. So you got many quality control options and you got many ways to analyze it. And this is, not very feasible in things like Grasshopper and all those other kinds of programs, because DesignBuilder is quite integrated. It will allow you to do all this stuff together. So use those tools as much as you can. One quick thing, if I can quickly do, Amanda, and that is that another quality control thing that you guys might want to try. I don't know if I showed you this, but we have a view called the model data grid view, which is like looking at the model like a spreadsheet. Okay. So what it allows you to do is that, for example, you can quickly check whether all the zones have got the right internal loads. You can check your inputs very quickly by looking at it like a spreadsheet. And if you've made a mistake, it's quite easy to edit it at that point. Okay, and you can save it. So once when you got a big model and there's lots of zones and you're trying to figure out what's going on, this is a really good way of working on models. We've been working on improving DesignBuilder since 2007, so we have had some experience now in doing some of these things for modelers.
You see, this is the best part of the DesignBuilder I find these days, actually, the spreadsheet part, I would say.
Yeah, all the old Do-To modelers, that's all they use. They'll do it.
So one question here, PC, the spreadsheet type window that you showed, is it only at the room level, or can we, change it even at building level or something?
Yeah, you see, it's at building level that it's most useful.
Okay.
Okay,
right.
but it will actually show you. So, for example, let's say glazing. Okay, so if I look at glazing, then it will load it by zone, but you can collapse different floors and zones and look at it for any particular zone. So here's my ground floor living zone. So you can easily see what is there. This wall is 0 degrees, so north facing wall, and here's all the windows on there. So you can easily go and check. Now, if you wanted to put like a different window here, it's easy to go and change it here also. So in the model, you can do a lot of work. And it tells you where you are. So block, zone, surface. Right now I'm on a surface.
Okay.
So, when you're navigating through it, it's quite useful to do that.
It can be done faster also.
Huh. And less mistakes. Garbage in equals garbage out.
Right. Yeah. All right. So yeah, that was the last question we had. So thank you, Mansi and PC. Thank you so much for a very informative session. And definitely it was very helpful. And I hope the participants are, they're ready to get started with shading and envelope using DesignBuilder. And thank you all for joining us today. So we do not have a webinar next week because you guys have to submit your first report or deliverable one. So all the best, and don't forget to contact with a TRG member if you have any queries. We will see you next week. Not next week. We will see you on 17th for the 4th technical webinar on water sufficiency for your building and occupants. So thank you.
Thank you.
Thank you.